All right, folks, let's start. Hello, everyone. This is Dr. Yuzo. Today is our 15th lecture for ECE 318, Electronic Circuit 1. Can you guys hear me well?
Yep.
All right, thank you, Shane. So we can move on. So the share screen here is presenting example 3 again. And before the very last example 4, also the most complicated one. Any questions regarding the procedure and the flow chart, which is equivalent but translated version of the procedure given in previous lecture? And also the example 1 through 3. Any questions? Anything? I think before the exam, at least before the exam, you need to go through them. Independently conduct the problem analysis all over again for example 1, 2, 3, as well as 4. That's the best way to prepare for the exam. But still expecting some, please expecting some difference. Okay, difference in the exam problem. Okay, won't be exactly same as any of these examples. So, any questions? Anything I can repeat over? Anything like those? All good? All right. Then let's take a look at the very last example. Yeah, very last example. Let's see. So very last example, as you see here, is a DC circuit, purely DC circuit. Okay. And there's no AC source, so purely DC circuits. So you don't have to find a DC circuit because the given is DC circuit itself. And what else do you find in terms of the difference from previous examples?
There's no capacitors.
No capacitors, yes, because as I said, this is purely DC circuit. Yes, no capacitors.
It's a plus 2.2 and a minus 2.2 instead of.
Oh, very good, very good. That's a very, very important point. A very big deal. A very big deal, actually. We have a not only positive but also negative supply. And this is looks like what the LPM circuit. Remember, we did in the lab. We have top positive voltage supply. We have bottom negative power supply as well. This is actually also commonly happen in the transistor amplifier circuit for different biasing. Then, obviously, a reasonable question is if given only one positive voltage supply, and then you design a DC circuit, and then give you positive and negative 2 power supply, you design a circuit to achieve the same operation Q point, DC Q point, you will have different resistance values. Okay, so they're all up to the constraints of your design. If the design is saying you only have one positive power supply, then you need to correspondingly design your circuit somehow just using that single positive power supply. Or the design is saying, well, I have both positive and negative. You might consider to use both. It's all up to the given. What do you have in your hands? What else? What else? You need to be very careful in this circuit. I think it's also very important to realize that this is what? P channel, right? This is the P channel. This is the matter. This matter a lot as well. This matter a lot as well. Not only the formula are different, but also what? You need to find the BSG loop KVL, right? BSG loop KVL, where is it? VSG loop, not VGS loop, because this is P channel. But where is the VSG loop? Up here. Okay, so you're writing KVL inside of this loop rather than the bottom loop here, because this is not the loop containing VSG. The upper loop here containing VSG from source to gate VSG. This is the VSG. Okay. So this is also very, very important. Okay. And besides, you need to know the formula for saturation current for P channel. And that formula I can provide here as ID saturation current formula is what, Kp, right? Not Kn. Times parentheses square, right? This is the saturation ID current. And inside of the parentheses, what do we have? We have V what? Sg minus Vt, not N, but P, right? Any questions? Because this is not right. Okay, this is not right.
Shouldn't
What's the
it
min
be
state?
plus?
Very good. Okay. It's plus. Okay, very good. So be careful. I know this is something you don't have to memorize because it should be on your formula sheet. You just need to copy and paste. But make sure you're copying the correct formula, okay, on your cheat sheet. Okay. This is the saturation ID current. Right? And later on, when you do the checking, what do you need? VSD, right? Compare with whom? VSD saturation, right? VSD saturation. By the way, trust me, it's very hard to write, use monster. And the VSD saturation voltage equals what? VSG plus VTP. Let me. VSG. Okay. I think you need these two equations. And other than that, but just to give you guys some time to come up with the equation first. Okay. Equations, you don't have to go further to the calculation, not yet. Just have the equations. Go ahead. Have enough equations, okay? By enough equation, it means you need to count, remember? You need to count the number of equations need to be equal to the number of unknowns. And you need to find the 3 unknowns, right? These 3. So you need at least 3 equations, and including all of them. All right, go ahead to come up with the equations as exercise. Go ahead. I will present the solution around 16, 17. All right. So before presenting the solution, so let's kind of recall the arsenal we have, right? For all of those weapons we can use. So first of all, we definitely gonna need this saturation ID current equation, right? For P channel. We definitely need it. In the meantime, we know IG is 0, open circuit here, and ID down here equals to IS up here. And both are what? Downwards. This is very important thing. Both ID as they're same, and also they both downwards. Okay, this is very important because the current direction determining the voltage polarity through the resistor, right? What else we can use? Like we mentioned, VSG loop, which is the upper loop here, KVL. And what else we have? Anyone remember? What weapon we have besides of what I just mentioned? Volt divider, yeah, volt divider is definitely very good. A volt divider and the past KVL. So combining Kevin and Daniel's answer, we got them all. We got them all. First of all, the volt divider Kevin mentioned is actually, this is the gate, right? This is the gate G. You will find it to write the ESG loop KVL up here. You definitely need voltage at the gate. Maybe with respect to the ground, maybe with respect to the negative 2.2. It doesn't matter, but we definitely need this voltage. Of course, inside of this loop KVL, what voltage we need is not the VG, but the voltage across what? R1. Does it make sense? That's another story, but the voltage is still relying on the voltage at the gate. Okay, so you have to find the voltage at the gate. A volt divider is necessary. And the last one, the past KVL, meaning this. Okay, Daniel meaning this. We're starting from the top positive 2.2, go all the way down to the bottom negative 2.2 through how many voltage terms? 1, 2, 3, right? 2 resistors voltage and 1 VSD, right? VSD, which is one of our unknown here, right? So these are the weapons we have. Okay. So by fully utilizing them, here, first of all, is the ID saturation current. And then this is the voltage divider. And then this is the VSG loop KVL. This is the past KVL. That's it. Enough for us to find everything. And here are the calculation results. So take a look. See any questions? How about first of all, because I think this is fine. This is just a copy the correct KP value, correct VTP value. How about second voltage divider? Does it make sense? Here, what I'm looking for is the voltage at the gate. Yes. With respect to where? Ground. So if you only just do voltage divider, okay, so which means the voltage total difference between VSS and the VDD, and positive and negative 2.2, and then we'll do a voltage divider to find the voltage here. That is the voltage to gate with respect to where? Negative 2.2, okay, not the ground. the voltage here cross R2 is the voltage from the gate with respect to the negative 2.2 rather than ground. How to find the voltage with respect to the ground? You need to add the bottom negative 2.2 volt. Does it make sense? This is how to find the voltage at the gate with respect to the ground. You don't have to do this. Do the calculation in this way, but if you follow my idea, find the voltage at the gate with respect to ground, and then go up here to do the KVL. What do you want to do? As I said, you need a voltage across R1. Okay, you need a voltage across R1, which is the voltage involved in this VSG loop to write that KVL, right? So who is the voltage across the R1? It equals to the voltage at this terminal of R1 minus the voltage at this terminal of the R1. Does it make sense? So the voltage at this terminal of R1 is equals to what? Nothing but positive 2.2 volts. And to be very, very careful, that 2.2 volts positive is the source with respect to what? Anyone knows? This 2.2 is with respect to where? Anyone knows? PE means speak up. Physical Earth or physical Earth. Well, to be honest, I'm not quite familiar with PE. This letter. I just know ground GND. Or you can use the 0 to represent, like I did here. So this positive 2.2 is with respect to the ground. That's why when you do the subtraction between this node and this node, you have to make sure both voltage are with respect to the ground, same reference point. Does it make sense? And that's why I'm using 2.2 minus the VG with respect to ground as well. And this is the voltage cross R1, okay, cross the R1. And then this voltage equals to the voltage cross RS plus the VSG. The voltage across the RS equals to RS times the current through it, which is ID. So this is how I end up with these two equations. Okay. And the last top to bottom pass KVL is obviously the positive 2.2 minus negative 2.2, just equals to the voltage drops through RS, RD, and the VSD. So these are the equations. And these are the equations. Any questions? And here we have questions. Zhu is asking, where does the E come from in the ID? E come from ID. What does mean by E? Where is
I think he's talking about for KP.
Oh, here. Oh, here. This. Anyone knows what does this mean? speak out. Let's be more efficient. This is this 2.
10 to the negative, like it's a power of 10. Wouldn't it be
That's
like
right. That's okay.
just calculator lingo?
Okay, okay. All right, all right. So some of you understand. So this is the equals to what? 0.035 times 10 to the negative 3. Or also equals to what? 0.035 milli. Right. Same meaning. This is E negative 3. I think MATLAB is using such way to represent the and the negative or any maybe positive 3 as well, using E, letter E. Any other questions? Does it make sense? Everything makes sense?
For the voltage divider equation, could you go over like exactly how you got that?
Okay.
I understand
so,
the. Oh, sorry.
Sure, that's fine. And so here, because in the KVL, first of all, actually, what I go is the KVL. These equations goes first, actually, because according to this equation, I can know which voltage we need, and then I go to the voltage divider to find it. So inside of this loop, obviously, you need what? This is 1 voltage cross the R1, the second voltage cross RS, and the third voltage is the VSG here. So voltage across RS is easy, ID times RS. Voltage VSG is one of our unknown. We keep it. The only matter is the thing is the voltage across R1. How to find this voltage across R1? Actually, you have more than one way to find it. By this method, I have is voltage across R1 equals to voltage at this node minus the voltage at this node. Makes sense. This is the basic voltage potential definition. Voltage across one thing is equals to the voltage potential difference between 2 terminals, right? However, the terminal here, the voltage potential is, as you know, is positive 2.2 volts. Positive 2.2 volts is the voltage at this terminal with respect to the ground. Okay, this is very important. It's not mentioning that way. However, by default, it's just the ground. Okay, given the power supply saying it is a positive 2.2 volt, it means nothing but between that node potential and the ground. Okay, by default. All right, this voltage at this node is 2.2 to the ground. And then I gotta make sure I find the voltage at the gate, VG, is also with respect to the ground. Otherwise, you can't do the subtraction. Does it make sense? So if this makes sense, then what you need to do is find VG with respect to the ground. But so if you simply do this voltage divider here, this big circle here, means the voltage here minus voltage here, total voltage cross R1 and R2, right? And then times the ratio in the numerator is the R2, denominator is sum of R1 and R2. What you got is the voltage at this, what you got, the voltage is from here to gate to here, which is the voltage across the R2. That makes perfect sense. However, this voltage across the R2 is equal to VG with respect to negative 2.2, not ground. Okay, because here, this node is not ground. This node is negative 2.2. Okay, so simply this voltage divider itself can only give you the voltage from gate with respect to the negative 2.2 volt, rather than the one we need, which is from the gate with respect to the ground. So how to find the voltage from the gate with respect to the ground? You need to add up your original reference, negative 2.2, here, the bottom here. Add, not subtract.
Okay, so you only tack on that if it's with respect to the ground and whatnot. You're basically just making an adjustment by adding the plus VDD.
Yes. Yes. So that
Okay,
you
that
can
makes sense.
find, yep. So that you can find with respect to the ground. Okay, this is the divider. But however, actually, you don't have to do it in this way. There's another way. Might be easier for you to understand. Let me present it here as well. This part, which including the voltage divider and the VSG loop KVL, could be solved in this way. How about this one? So in this loop again, we were pretty clear. Once again, what we need is a voltage across R1. Okay, voltage across R1. How to find a voltage across R1? But this time, voltage across R1 is actually the voltage between the 2.2 and the gate, right? How to find it? But directly apply this voltage divider. How about that? This voltage is just equals to this simple voltage divider. Does this make sense? Numerator now is R1. It's not R2 anymore. Okay. And by this simple voltage divider, what you got is the voltage across R1, exactly what we need, and then place it into the VSG loop KVL. Done. Alternative way to solve the same thing. It might be easier to understand. Any questions? Any comments? That way seems clearer. Maybe, however, I still prefer this complicated way. This way is showing in-depth understanding of the circuit, electronic circuit, in my opinion. But this way absolutely work. Absolutely work. If you feel this way is easier, okay, you can apply this way. The bottom line is you're fully aware that in this KVL loop, you need a voltage across R1, which is from 2.2 to G. You need to find this voltage. Any questions regarding the equations? The rest of the thing, algebra. Any other questions? All right, if no questions, give you guys maybe 3 minutes more to finish the rest of the work. Go to the checking yourself. Try to checking yourself. Go ahead. All right, let's see the. So first, the VSD is, as we calculated, 1.797. And then we need VSD saturation voltage, which is following the formula we discussed earlier. And by comparison between them, obviously it is saturation operation. Okay. So we are done. Now we are done. Yeah, just simple like that. Just simple like that. Any questions? Any questions regarding this example 4? One more time, the key is item mass. The key is this, okay? The first, you need to realize, okay, this is a P channel. Second, you realize the VGS or VSG loop KVL should be up here. Third one is inside of this KVL, you're looking for the voltage across R1. How to find the voltage across R1? The voltage divider, you need to be careful. So these 3 things, okay, 3 things. If you are clear or be careful enough about the 3 things, and then it should be fine. It should be fine.
I'm sorry, I had to go reset the router. It was confirmed the assumption was correct, right?
Yes, yes, yes.
Okay, cool.
Did you see this solution?
No, I didn't, but that's what I got.
Okay, yeah, I thought you missed this part. So this is the solution. It's not something difficult. The rest of the thing, not something difficult. And then we go back here and emphasize 3 things you need to be careful. First, you need to realize this is a P channel. Second, you realize where is the VSG loop so that you can write a KVL 4. Okay? It's up here, not necessarily bottom here. Okay? So you need to read. You need to read a circuit to know. Third thing is be careful, the voltage divider. Okay, voltage divider. You're looking for the voltage of across the resistor involved in that VSG loop, rather than the voltage across the other resistor R2. No, that voltage across R2 useless. We don't need that. We don't need that. We need a voltage across R1 here, because that voltage is part of the KVL in this loop. Any questions regarding DC nest? Basically, 4 examples covered, I believe, every details could possibly happen in the exam. If you have caught all of them, then should be okay. All right, if no questions, we can move on. Here is introducing the concept of multi-stage MOSFET circuit. Multi-stage, okay. And they first is saying transistor amplifiers are frequently connected. For what? Multi-stage circuits can provide greater overall voltage and current gain, improved linearity, better input and output resistance, etc. How to understand this? First of all, why we are connecting them? For example, just a generic diagram like this. We are basically, this is what, cascade or say series connected, right? The output of the previous stage here is the input of the next stage here. And then the total output is V0 here. So from here, obviously, who is the total gain now of this connection? Is this total output over this input, right? Stage 2's output over the stage 1 input is the total gain, right? So why we are doing this connection first? We're gonna have an overall bigger, greater gain. Why is that? In other words, this is the question, right? This is the question. What is the total gain now? Stage 1 has gain of AV1. Stage 2 has gain of AV2. What is the total gain? AV1 plus AV2, right? Any questions? So listen up, everybody, and listen up, everybody. This is absolutely wrong. Okay? AV1 connect to AV2 in such a way that the output of AV1 hook up to the input of AV2. The total gain, resulted gain, is not the sum between two gains, but what? A product. So the total gain, the correct total gain is AV1 times AV2. So remember this firmly. Okay. It's something you need to really understand. You need to really understand. It's a product, not the sum. Okay, this is absolutely so. Anyone knows why, actually? Anyone knows why? Anyone know why? Or any guessing? Any thoughts? All right, let's derive this. Okay, let's derive this. How to derive this? First, define the middle signal here as Vx. How about that? So first of all, Vx over Vi equals to what? Anyone? Vx over Vi equals what? What is it? Anyone not there?
Wouldn't that just be the gain of AV1 or AV1?
Which is AV1 itself. Yes. And then what? V naught over Vx equals what? Same thing, right? Same AV2. This is the definition for each stage. The definition of the gain for each stage. And then what we're looking for is this guy, right? What can we do? This guy, how about equals to V naught over Vx times Vx over Vi? What do you see? Cancelled, right? And this guy is what? AV1. This guy is VV2. So AV1 times AV2. Times, once again. Does it make sense?
Yep, makes sense.
All right. All right, if this makes sense, then shift button. And then we can move on to next. Better input and output resistance. This is also very important benefit by connecting multiple stages. So what does it mean is, for example, if you only have stage 1 itself, and then you need to make sure the input impedance of it big enough, output impedance of it is small enough. But if you use multiple stage, what you can do is you just make the stage 1 to be a stage taking care of the input impedance, nothing else. And make the stage 2 as a stage taking care of the amplification. Maybe you need a stage 3 here to take care of the output impedance. So 3 stages are perfect. In where only stage 2 is take care of the majority of the gain. The rest of 2 stages only taking care of the input and output resistance, respectively. Because you will see that the different amplifier, different common circuits have different feature. Okay. The only common source amplifier has big enough amplification gain. Okay. The common drain, the common gate, they don't have big enough amplification gain. It's not able to contribute gain a lot, but they have very good either input impedance or output impedance. That's why they are also useful, okay, because they could be used as the front end or the back end stage. Does this make sense? Because input impedance, output impedance is very important. Okay, they're really important. They're really important. Okay, because of the loading effect. Because of the loading effect. This is we had 2 multiple choice problem in the midterm 1. So keep this in your mind. So without taking care of the input and output impedance, your gain is terrible. No matter how big the gain you're designing is useless without decent input and output impedance. Okay, you see that. All right, here we have basically 2 types of connection. One is called cascade, the other is cascode. They pretty much the difference is orientation and also different type of common MOSFET circuits. The common MOSFET circuit. Remember, we learned we have up to 3 types, right? Because we have 3 different terminals, right? GSD. So we have CG, CD, CS. Common gate, common drain, and common source. Anyone remember how we differentiate them? How can we tell which is which? Anyone remember what's the rule? How can you tell it's a common, say, common source? How can you tell it's common source? Anyone remember how to tell which is common what? A little bit hint here. So first you're looking for what? The input, right? And then you're looking for what? Which terminal is the output, right? And then what? The left, the third terminal is the common terminal, right? Remember that? Any questions regarding that? If that is clear, then we apply that rule onto this first one. The first one is cascade. The first one is cascade. This guy, cascade. And you're seeing MOSFET 1 and the 2 stages, right? So by watching the circuit, what is the common circuit for M1 and what is it for M2 respectively? And also to second cascode, also 2 stages, M1 and M2. They are respectively common what? So let's take this list as M1 in cascade. So this M1 is common what? Anyone can tell? Common what? And why is that? Anyone remember what we learned? M1 here in cascade is common what? And why? You're pretty much just looking for the input terminal is occupied by whom. Output terminal is whom. The left terminal is common terminal. Right? Anyone? M1 is what? Come on, folks, it's too quiet. M1 is what?
Is that source because the VI positive is going into the gate?
And?
That's all I got.
That's all you got? Well, I mean, you got an input, and then who is the output then? The next day is looking for the output. Who is the output? And therefore, you can decide who is the third one, common one, right? You reach the final conclusion is common source actually is the correct answer. And then going back, who is the input? You're right too. The gate is the input. Because it is connected to the input, of course, it's occupied by input. Who is the output?
Would it be the S terminal on M2 is connected to the output?
Here is the output correct. However, this is the output of M2.
Okay,
Now we are studying the M1. Who is the output of M1? This is actually the nature of the question.
Would that be the drain?
Why is that?
Because
yes.
it looks like it's going to the gate of M2.
That's right. It's okay. So this is the connection between the stage 1 and the stage 2. So it's definitely the output as well as the input of the M2. Right? It's definitely the output of M1 and also definitely also the input of M2. Does it make sense? So this is the connection in between, 2 stages in between. Okay. Of course, it's the output of the previous stage and also the input of the next stage. Does it make sense? Therefore, input is gate, output is drain. The common terminal is the source here. So the first one is common source. For the same reason, the second M2 is what?
Common drain.
Common drain. What is that? Input this time is gate.
Gate.
Output
Source.
we have identified as source. So it's a common drain. The common drain is also called SF. What does it mean by SF? S is our source. F means follower. Okay? S means follower. Source follower. Okay? It's also called that way. Does it make sense? This is very important. Okay, correctly identify what type of the amplifier it is, because in the exam, I think we are going to have a problem like this. Identify the given circuit is common what circuit. Okay, you need to understand, because previously we learned how to identify first of all the terminal, and then we learned how to identify the type, right? The channel, N channel or P channel. Now we are learning the third identification we need to be able to do, which is identify the common terminal, common circuit. Right? I'll move on to the test code M1. What is it? Two, what do you think? I have to pick up particularly someone to answer. Two, what do you think? M1 is what in test code? Two, are you there? Any answer then? M1 is what? What do you think? Speak out. Don't type. That's wasting a lot of time.
Is it the input?
Say that again?
Is it the input?
No, I'm asking M1 is common what? Drew, what do you think? Common drain? Why is common drain? Just a guess? No, you can't guess in the exam, right? Otherwise, the performance, the grade is going to be disaster. You need to mute. You need to mute.
Is there such thing as common gate, or is it only source and drain?
You mean M1 is common gate?
Yeah, I
Or
was
what do
just
you mean?
I guess I missed the portion earlier when, like, previous to this lecture, when we were talking about common source, common drain, etc. So is there a common gate as well, or is that not a thing?
Yes. 3 terminals, so you have up to 3 types of common circuits.
Okay. So do you want two to make the guess, or can I make the guess? Or the educated guess, anyways?
No, you don't want to have a guess. We prefer to have reasoning without the conclusion than guessing the conclusion without any reasoning. You know what I mean? So, Daniel, what do you think? M1 is what?
I was also thinking common drain.
M1?
Yes.
What's the reasoning? It doesn't
Because
matter if it's right or wrong. Okay, what's the reasoning? Let's see.
it seems that the source is being used as an output.
The source is being used. The source is being used as output. What does that mean?
Like it's the drain of M1 is connected to the source of M2.
So I see. You guys are not is not getting. Everybody, listen up.
Yeah.
How we tell this? Okay.
I would. Oh, sorry.
That's fine. And maybe Shane has get it, but I still obviously need to repeat how to do this. Okay. Everybody, listen up. Okay. Pay enough attention. Okay. All right. Let's take a look at how to do this. Okay. Going back to here, what we do is it's a two-stage, right? Two-stage, M1 and M2, representing two different stages. Okay, and then how to tell the common circuit? We are telling stage by stage. You're not telling the overall circuit is multiple stage circuit. We're not saying the common terminal for the entire circuit. No, we're talking about individual stage. This is the first point. Therefore, we are looking at M1 individually, and then followed by looking at M2 individually. So if you're looking at M1 individually itself only, you need to identify who is the input terminal. Input terminal is the input, the VI given to this input terminal, which is gate. Who is the output? Output is a little bit hard to be identified. However, you see this is two-stage, so you have a connection between two stages. This connection is the output of previous stage and also the input of second stage. Does that make sense? Because this is what we learned from previous slide. Output of the first stage is also the input of second stage. So this is the connection between two stages. Same thing here. Therefore, this connection is definitely the output of the M1, which is the drain. Input gate, output drain for M1. Once again, M1. Okay, we're looking at M1 and M1 only. Okay. And then the left terminal for M1 is the source. So this is a common source. To M2, again, we are looking at M2 and M2 only. The input has been identified previously. It's the connection between the stage 1 and stage 2. So it's a gate. M2's gate is the input terminal. The output is very clear. The output is labeled as V0. This is a source. The input gate, output source. This is what? Common drain. The third one left is the drain. Right? Same thing applied here. Now, M1 is what? And what's the reasoning?
I would have to say it's a common gate because it looks like the input is coming from M2 and the output is through the source.
Oh, I see why you guys don't get it. Obviously, Kevin got it. And the reason some of you are not getting it, I think I got it. Why you can't tell. How to identify the input of the first, or say how to identify the first stage from the second stage. You need to see the total input of the entire circuit, right? Who is the total input of the entire circuit here? You only have one input, VI. VI now is not feeding M2. It's feeding M1. M1 is the first stage. If this is clear, you guys go ahead to see if you can reach the same conclusion as Kevin did. Because Kevin here is pretty much presenting the details why. So what matter is, can you reach there too? Is better?
So what you're saying is the plus 5 volts and the minus 5 volts are less important. It's essentially VI that we should be focusing on.
Oh, this is regarding the concept I emphasized before. For positive 5 and negative 5, they are power supply. I never call them as input. They are not the input. They are power supply. You don't want to consider or understanding them as inputs either. Okay? They are not. They're just providing external power.
Okay.
Okay, we never call them input. They're not. Okay? Calling them input is very actually easy to confuse yourself. They are not input. Good. Obviously, Shane got the point where he probably wasn't very clear. Great. Okay, that's great. That's how the learning is happening. Good. Daniel, what was yours?
I think I was just getting confused by the power supplies as well.
Okay. Good. Power supplies, remember, we never call them as input. Well, back to the cascade. We never talk about the power supply either, right? We're not talking about it. We never talk about it. Okay. We never talk about it because we don't call them as input. They're just an external power supply. They're not considered as an input now. Input to a multi-stage amplifier is unique, right? Only one. Does it make sense? It just or say going back to DC, only one. VI is the input. Of course, stage 1 you have a power supply up here, maybe also second power supply down here. Stage 2 power supply here, maybe also power supply here. Or once again, just the external power they're not even presented in the generic multi-stage amplifier, right? So the output, total output, unique, total input, unique too. Okay, so no. DC supply, no, they're not in our picture. Just supplying the power. They're supplying the power. I think is a little bit inertial issue. I mean, right after DC analysis, we can't forget the DC, right? But actually, no. This when you talk about amplification, you talk about amplifier circuit, it's not DC anymore. Remember, AC small signal is about amplification. By the way, what the DC analysis for? Anyone remember that? They're a DC power supply. They're providing the external power for the amplification. But what we are conducting or designing the DC analysis for? Anyone remember? This is about something we learned. Say that again, Kevin.
It's to confirm we're in the saturation region and actually doing amplification instead of
great, excellent. Remember the reason. Okay, remember the reason. And also, no, it's 12, but 11, I think. I show you the PowerPoint slides where I emphasize this concept. Here, remember? DC analysis is trying to locate your Q point. Okay. Make sure it is inside of the saturation region. Without this, it's not even guaranteed in saturation region. It won't work as amplifier. So all of these concepts either confirmed or somehow related, okay, through the entire course. Come back to here. As Kevin said, common source and common gate. If you go into the details, well, also like he just said, to M1 individually, Input is the VI. Output is the connection with M2, which is the drain here. This is the connection. Leaving the source terminal here as a common terminal. It is hooking up to the -5. So what? Okay. We are not care about what is connecting what. That's the look. We don't care. We follow the rule, the principle. The input is for input at the gate. Output is connection with next stage, which is the drain. Left terminal is common terminal. Connect to ground or connect to a power supply. Doesn't matter. It's common source. And then move on to M2. Input we have figured out. It's just what? The thirds of the M2 is the input. Output is what? Output is labeled as drain. With a common terminal. The left one, which is the gate, the common gate. How does connect to the ground? Well, I don't care where it connect to. It's the left one, left reference common terminal to both input and output. So it's common terminal, common gate.
I guess the other thing I was getting tripped up on, that this is what screwed me up, is the direction of the arrow for the MOSFET. I was thinking that since the arrow is like what a N channel in that case, since it's coming out of M2, I was thinking that was the input of M1, and I think that's where I was getting screwed up as well.
Oh no, I see. So current, yes, its current flowing is this way. Current flowing is this way. But the current still is the DC current, right? Still the DC current. And amplification here we are talking about is actually regarding the AC. And that's why this is the end of the DC analysis. I'm trying to bring up something also related to the AC analysis right after. Yeah, it's like I said, I think this is more of the inertial thinking. There's a big inertial just right after the DC analysis. Okay. Once again, amplifier, multiple stage amplifier. Remember, input is AC, and we forget about the DC. DC is something we have done before that. Remember, we need to conduct the DC analysis first, followed by the AC analysis. Since we are mentioning the amplifier, looking for the gain, etc., right? The multi-stage gain, total gain. It's already AC. It's already AC. That's right. I think Shane's concern makes sense too. If you're looking at a current, it's a current flowing downwards, all the way downwards. So it's very easy to think the input of the M1 is the drain. No. However, it's not that way. It's not that way. Input means the AC input is given to where. Very good point. Very, very good point. Very, very good point. Hope everybody are not only following my explanation, but also trying to follow how other students making mistakes. Okay, this is how the real learning is happening. This is real learning.
Yeah, it makes a lot more sense now. Thank you.
Sure, absolutely. Thank you for bringing up these details. Okay, good. Very good. A couple of minutes left, and any other questions?
Just what Shane said about the arrows of the current, I think, was a big thing in trying to understand it.
Yep. I agree. I'm aware of this as well. Yep, that's a good point. Very, very good point. Very, very good. Very, very good point. Yep. The input, yes, this is a little bit hard to understand this. Because if you look at the current, yes, it's downwards. However, the input is down here. And the sort of is going upward, right? The output is up here. The input is down here. So that's the thing. That's very, very easy to be confused. Yep. Very good discussion. That is a very good discussion. All right. Any other questions? Other thoughts? Once again, okay, this arrow is DC current. Okay, DC current. AC current. By the way, I think it's interesting to discuss why we don't talk about the current direction in AC. Anyone knows why? We can't say the current of the AC is up, is from here going up. We cannot say the current is going from top to bottom this way either. Anyone knows why? Kevin?
AC stands for alternating current, so one
Excellent. 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 What Kevin is talking about is this. Okay, obviously, he is holding very clear concept here. For AC is what? Sometimes it's flowing one way, sometimes it's opposite the other way, right? So the current direction arrow here is not helping. It's not helping anything. Only indicating the DC current is flowing that way. That's 100% correct. Great. Great. Not only Kevin, okay, but also Shane's point. Very, very useful. Very, very useful. All right, I think that's all for today, and thank you everybody's attending today, and talk to you guys next week. All right, have a good weekend. Thanks, you too. All right, bye-bye.